I don't mind if you draw it, but I don't.
No, it's not like a drawing.
Okay, good.
Like,
all right, so good. Can we do this? Anyone want to like help? Grab a marker. No one wants to help. Good. Here, take blue. Take blue.
Circle and draw a square in it.
And then here I'm free to use here and here. This could be anything purple, or you take the green. This has to be like red or blue. And then this could be red. This has to be red? No.
No, it doesn't.
This has to be blue though. Note that this one has to be blue. And what's up? This one has to be green. True. This can be anything, I think. But then this one has to be red. All right, that was not much of a challenge, to be perfectly honest. Okay. Anyway, this person seemed to notice always that 4 colors only were required. And he posed this as a problem. It became known as the 4-color problem. Can you prove that the regions of a plane can be colored with just 4 colors, such that regions with adjacent colors have, or adjacent regions have different colors? All right, a lot of these proofs turned out to be like crap. And what was eventually realized is that this is best understood as a graph theory problem. And in fact, what we should do is convert this away from regions into questions about colored vertices. And so what we're now going to do is I'm going to do something called producing the dual graph. The dual graph says place a vertex at the center of it, or just anywhere really, inside of a region. And now the information about 2 regions sharing a border is going to be captured by making the 2 vertices adjacent. And so I will connect these 2 vertices because the region that these vertices share a border. And I'll connect these 2, and I'll connect these 2, connect these 2. These 2 also share, does everyone see what's going on here? These 2 share a border, so connect, 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 connect. And what we're doing is we're basically like putting an edge between every 2, well, that's exactly what I'm doing. It's just the definition of the dual, and there we go. Did I miss one? And
Same purple. Yeah, that's 3 purples. There's another blue. And another blue circle. Between those 2. Just all the blue. Except for black.
whoa. Okay. Am I done now?
No.
Really? Wait a minute. I missed another one? Oh, she's so right. Good. Note that every for every sort of door between 2 regions, I've now like put like an edge between them. Okay. I now have a graph, and now once again, the sort of moral of the story is that I can now abstract away from the particular messy, disgusting geometry of these various regions with their weird, ugly shapes, and I can now just say a graph, or rather a map, can be colored if and only if its corresponding planar in this corresponding graph can be colored. Yeah, I'm going to define dual in a second. But basically, this is now a discrete math problem, which is given. Can everyone now like mentally erase the map and just look at this graph? Now the graph theory problem becomes color all the vertices of the graph in such a way that no 2 adjacent vertices have the same color. This is called a graph coloring. A graph coloring is the problem of coloring all the vertices of a graph in such a way that no 2 vertices have the same color. All right, and yeah, good. So I'll come back to that in a second. So the chromatic number of any graph, the chromatic number of a graph, and this is usually called chi. So So chi of some graph G is the number, it's a shitty chi, that's alright. The number of colors required, the number of colors required to, there's a word I'm missing, to properly color it. So this is called a proper, apparently he calls it a proper coloring. So a proper coloring of a graph is a way of assigning colors to the vertices of the graph such that no two adjacent vertices have the same color. And the chromatic number of a graph is the minimum number, I should say, because you could always use more. The minimum number of colors required to properly color it. Okay, so let's just do a couple graphs and see what their proper coloring is. Well, how about something like the complete bipartite graph? Yeah, she just immediately says every bipartite graph has chromatic number 2, right? So the chi of any bipartite graph is 2. In fact, that was something we sort of used coloring already to kind of talk about bipartite graphs, right? How about something like K5? How many colors are required now? I think 5 are required, right? Because taking any vertex, for example, if it's one color, well, the 4 other colors all have to be different. So the chromatic number of K5 is going to be 5. And okay, in general, if you give me some graph, like here, I'm just making up a graph now, and it looks like this, and like I don't know, some crap like that. Okay, great. What is the chromatic number of this graph? What do you think?
4. I don't know. It's 3.
There's like one vertex that has
Let's add some more crap in here and just to make it a little bit more exciting. Whoa.
It's 5.
5, really?
Wait,
No,
no.
surely not.
3.
Surely I can do it in, I think I can do it in 3. Yeah.
Wait,
Yeah.
we can make it a 5?
I think I can do it in 3, right? Arbitrarily let that be blue. Then, without loss of generality, let that be green. Let this be red. But then, like, I can also let this be red, right? Yeah. And then this top one can be green. And then this bottom one can be, well, green. Okay, so what I have just produced is an explicit proper coloring of this graph. Now I have not actually determined that the chromatic number is 3. What have I determined specifically about this graph? Right, so that what we would say is that the chromatic number is less than or equal to 3, because the chromatic number is defined to be the minimum. So since the chromatic number is defined to be the minimum, if you want to prove of a particular graph that its chromatic number is something, you have to, I have to say something like, what am I trying to say now? To prove,
It's less than or equal to 3, and then it's greater
and then it's like greater than or equal to 3. So I have to argue that this can't be colored in fewer. That's right. I have to argue that this can't be colored in fewer than 3 colors. That requires like a proof. And I have to show that it can be colored with 3 colors. The most straightforward way to show that it can be colored in 3 colors is just to produce a 3 coloring, which is what we've done. Now let's argue that 2 colors are impossible.
Look at 1.3. I found a cycle.
And there's a cycle of...
Yeah, there's just a cycle. Boom, there you go, right? No.
It's K3. It's the fact that we have
A complete graph of
Oh, it's like that there's a K3 inside of it, yeah. And these all, okay, even simpler, like, right, like this is blue. Yeah, I guess it's just, it's that, right? It's like take these 3 vertices, which is what he is calling the K3 subgraph, right? Because there's a, so sort of like theorem, right? N colors are required to properly color Kn. And so the complete graph, so this requires 3 colors. And And so therefore, if any subgraph, yeah, okay. Woo! All right. So the dual. Oh boy. Yeah. Oh well. It's okay. We're only just a couple hours short. Yeah. So notice how what I started with here was just some sort of arbitrary number of regions. But what we often want to do is take some sort of graph and talk about the coloring sort of induced by that graph. Now, the thing is, the very concept of region in graph theory only makes sense if the graph is planar. And so if G is planar, and only if G is planar, then we can, and I'll now just draw some kind of planar graph. So, having fun, drawing what? Having fun, drawing a planar graph, and well, great. Here it is. Okay, and so what the question is, can if you have a planar graph, then you have a certain number of regions. Here we have 1, 2, 3, 4, and 5 regions on the outside. And now we can, what we can do is ask, how many colors are required to color all of these regions. And what we have just seen is that the best way to answer that question is to produce the graph in which we put a vertex in the center. And so we have a name for this process. This process is called duality. So the dual of any graph, of any planar graph, is the graph that results from placing a vertex in each region and connecting those vertices if the regions are adjacent. Is there anything better than that? Nope, that's it. So let's just do it. It gets a little bit complicated though, because one of the regions is like outside, right? So here's like this outside region. So these two are connected, so they share an edge. These two are connected because they share an edge. But then like this region is connected to the outside, right? So we need like a that. You could go whichever way you want, it doesn't matter. No, you can't go inside, you gotta connect. It's like you have to abstract away from what we're doing is we're replacing each region with a vertex, and we're replacing the borders between any two regions with an edge. But notice that you don't always get like a simple graph, because this region contains two, right? There are two borders between this region and the outside region. And so what you need to do is you need to go through every door, man. I connect these two because this region was connected to the outside, but this region had another connection to the outside. And what else? This one needs to go here also. I'm not sure if I should have put that dot there or not. Then this gets kind of weird as well, because what? Oh my god! What do I do with this weird edge here?
Is it like?
Not only do I have to do this, but yeah, this region, this edge, like, is the border between the outside region and itself. Yeah, so we need like a loop.
Oh, you make it go through? What?
You make it go through. I mean, the actual, the graph is the graph, man. So like, well, but what I wanted to do is to like visually confirm that I'm done. Because have I crossed through every door?
Sure.
Like that's how you know you're done, and you didn't miss any, right? Like I killed every edge. Does everyone see what just happened? Okay, cool. Say cool. Okay, so this blue graph is the dual graph of the original planar black graph, right? Because I have a couple things to say. It only makes sense to talk about the dual of a graph if it's planar. Because otherwise you don't have regions. And what is the degree of this vertex out here? It's 1, 2, 3, 4, 5, 6, 7, 8, 9. But that's because this outside region shares 9 borders with other regions. And so there's like this sort of duality between bounding edges and degree of the vertex. The degree of any vertex is the number of bounding edges of that region.
Why do we care about all these extra edges? This one, it doesn't.
It's not, I don't think it's directly related to coloring problem.
Wait,
I don't know. Yo. Yeah, then there's also like polyhedra duality. More on that next class. All right, some homework on. There will be some homework on colorings, duality, polyhedra, and that's it. I'm going to see you guys for a half an hour on Tuesday.
Yay.
And then we're going to have a test on this unit. It's a little
Will
rough.
there be like a